Okay, welcome everybody. Bayes, we're going to be talking about mixture sampling and mixture inference in just a moment. I'm going to tell you the Gibbs sampling procedure for doing this. We'll walk through the steps. I'll explain to you that if we knew something, everything is easy, and then I'll tell you how we can learn that something. We have a final coming up on Friday. I'm going to give you guys until Saturday to turn everything in. So the protocol is going to be on Friday. I will give you the final at some point. So I'm not going to send it out at 12:01 in the morning or anything like that and say you've got 24 hours. So I'll send it out, maybe around 10 a.m. on Friday. And you'll have until 48 hours, I think, is reasonable to get me everything. So you'll submit everything by 10 a.m. on Sunday to me. Extra credit projects and homeworks go to Sierra. So send everything her way. If you need to communicate about something on that, Sierra's got you. So again, this is the big crunch where we turn everything in. You've got plenty of time to still work on everything. I will say this. If you want to code up what I'm about to show you for the example that we studied in homework, so we had a homework assignment that was based off of mixture sampling. If you want to code this up and write me a 2-page write-up on inferring these mu's, you can let sigma be known if you'd like for that example. If you understand what I'm saying and you know how to code this up at the end of the day, you can send it over 10% midterm credit. So I would probably do this one because it's relatively straightforward. Behrens-Fisher, you probably have to watch a couple videos that we supplied you with, but this would be easy 10% credit. I'm not sure if we'll have time to get into empirical Bayes, but if I can get through this quick enough, I'm going to show you another Bayesian strategy that I used to not like at all, and now I have a fair amount of affinity for it. So there's cases in which I'll do it, but there's cases in which I wouldn't touch it. Really cool properties though, and some cool take-home messages. So I'll try to get underway. Let me just remind you, a mixture model looks like this. So where I've got some density function and I've got some probability weights. So these pi k's are probabilities of being in component k. And when I'm thinking about component k, I'm thinking about the kth density function. The density function could change. I don't have that labeled right here. So I think in general, you could let the density change entirely. But for my example, I'm just going to let the density functions be the same parametric family, but I change the parameters within that density function. So let me give you the example. This is straight out of the homework. Our density function is a normal distribution, and each component has a different mean and variance. In your homework, we let that be common. I think I let that be 5. So I'm going to talk about it a little bit more generally. But if you are doing the extra credit, you can let that be known and just set it to be whatever it was in the homework. I think it was 5. So mixture sampling is just repeating a process of flipping a coin. So I'm writing this down as a k-sided coin. A k-sided coin flip to a statistician or a probabilist is a multinomial distribution. So what I'm going to do is I'm going to flip the coin and figure out which component I'm in. I'm going to flip the coin with the probabilities that are acting as weights on that density right there. So I flip the coin, and then once I have k, one of the sides, so if it were a 4-sided coin, I flip it and I'm going to see a number that's between 1 and cap k, 1 and 4. So let me just write that down. So this is an element of 1 to cap k. They're just labels. So I'll say they're labels. And if you're from the supervised learning community, I'm using labels is the same way you would be using that word as well. And so I'm labeling my data. Once I have the label, then I generate an X from that particular component. And so I just draw I draw from a normal distribution in our example. Now I will say, if the weights are big right here for some of the components and they're small in other components, these modes would be going up and down. And so they would be bigger or smaller. I kind of drew it that they're all very similar. But let me just give you another illustration, since I don't think my picture is all that good right here. So let's imagine pi 1 was equal to 0.1. Pi 2 is 0.3. Pi 2 is 0.4. So that's 0.7, 0.8, and then we've got one more. Pi 4 has to be 0.2. So if I were to draw a whole bunch of samples from this, I just keep repeating this process, I get something that looks like this. A histogram looks something like this. So a little bump right there, a bigger bump, an even bigger bump over here, and then this one would be relatively small. So this is going to have 20% of the mass under this curve. And this is going to have 40% of the mass. Under there, 30% and 10%. And so that's going to be associated with these weights. You'll notice, even though I didn't draw this overlapping too much, there is overlap in all these tails. And that's where the confusion really occurs. And so if we knew what the labels were, if we got to see both the ki's and the xi's, sampling, or I would say learning the parameters is easy. So the name of the game in statistics is you get data, and then you try to learn what the function was that created your data. And then you do something with it. Either it has inferential value to you, or maybe you'll use it to forecast. So lots of things that you can do once you learn what the process is. So if I got to see the k's, this eraser is getting terrible. I'm going to grab a piece of paper. I can make some progress on this a little bit. We'll make do. So if I did get to see the ki's, so let's say I ended up knowing how many of these things, after I sample, I goes from 1 to n times, I repeat this process. Let's say the number in component 1 was something like, I'll say, I'm just going to call it n1. So that would be the number of draws that I have in component 1. So if I repeat this process over and over again, I would just count up the number of times that I see ki being equal to 1. I'm going to let that be n1. And similarly, I'll say the number in component k in general is just going to be nk. So every time I see a number 2 out of this sampling, I just increment this number. And so the n1s, the n, I'll say k's. K goes from 1 to cap k. This is equal to n. So the number of samples. So that just gives us a little bit of notation. If I got to know the ki's, I could figure out what that number was. And so what I could also do, if I do the ki's, is I could separate out the x's. So I might say x k is going to be equal to the collection of x's of xi's from component k. So in my picture, maybe all of these data points right here were collected from component 1. And so x1 would be all of those points. If these were the only points coming from component 4 right here, then I'd be calling that cap x k. So just to keep with building some notation, I'll say x k's, and I take a union over all of them. K goes from 1 to cap k. That's going to be your full data set. Okay, so if I knew what the k's were, I could compartmentalize everything. And doing inference would be very easy. So if I want to learn what mu1 is, then all I need to do is use the data from x1. If I wanted to learn what mu2 was, I just use the data in x2, cap x2, so on and so forth. So we would just do what we already know how to do. I might build a Gibbs sampler to learn all of my parameters. So let's write down what that sampler would look like. We in the department have purchased these fancy-dancy glass board markers, and we've been told specifically to only use these. Unfortunately, they don't work either. Technology. So this is sometimes why I just like the whiteboard. Or I like the blackboard, the chalkboard. Okay. So what I would do if I got to see the k's is I would just infer as a Bayesian, let's say mu, let's just say for each k, infer for each k, it's an element of 1 to cap k. I would infer mu k and sigma k. I would probably put this on the precision scale. So I'd say this is 1 over phi k, where that's the precision. It doesn't matter. You just have to do the inverse analysis if you didn't do that. So we've been keeping with the precision parameter, so I convert my variances into precisions. This is going to be sigma squared. So 1 over sigma squared is the variance. What I would do is I would infer these from its posterior distribution. So pi, mu, and phi given x k. So I just condition on xk right here if I wanted to learn those. So for component 1, I would compartmentalize all of my data in component 1. I'd be able to do that because I know the k's, and then I would be able to just build its posterior distribution. What I would do to learn both of these parameters is I would build a Gibbs sampler. So my Gibbs algorithm might look like this. For component 1, or I'll say component k. So mu k, phi k. Let's just do this sequentially. Do it again. It's a little bit better. What I would do is I would run in a for loop some large amount of times. Large is not 100. Large is something like 1 billion. Realistically, 10,000. But what I would do is I would sample mu k from its posterior distribution, pi mu, given phi, and all of my data from component k. And then I would have some indices on this. This would be given t minus 1 for the kth variable right there. So I'd be conditioning on this. You'd need to initialize your Gibbs sampler so you had something to pull in there for your first iteration. And then I would update phi k. And I would update that from its full conditional distribution. I'll just let that be a dummy argument. Then I'll say this one is conditioned on what I just sampled. So this sample. Plug in there. And I would condition on xk. And I would do this for each k. So what I insert right here is a for loop. For k goes from 1 to cap k. And I would end that for loop here. So I just do that for each k. I would keep running this thing. I would store a whole bunch of stuff. I would look at the trace plots. I'd make sure everything converged. I would reinitialize everything. So there's an initialization step right in here. In our cases, we just need to initialize the phi k zeros because it's the variable that I'm conditioning on first. So I'd initialize all of those for k goes from 1 to cap k. I would change my initial values, and then I would see that it converges to the same thing. I've got a question, so I'm going to try to read this. Okay. Somebody asked, why would I update the fees? In the homework project, you don't have to do it. But in my problem, I'm going to explain this more generally. So I'm explaining this more generally so that you know what to do if you didn't know the variances. And so I'm going to keep this general for your extra credit problem. If you want to do it, you can assume that it's known and then you wouldn't have to update it. Hopefully that answers the question. So just because I'm talking about this more in general. You'll notice in all of this that I'm talking about, I'm saying this is known, cap k. So if you didn't know cap k, you would have to do something else, and you would have to learn it as well. That would be another line in your Gibbs sampler. So if you know things, you don't need to update them. If you don't know things, you have to update them. So that's the answer. I'm going to assume that's known, though, in this illustration. So an advanced Bayesian class might teach you about Dirichlet processes. Would teach you how to play around with this if this is unknown. Okay. So hopefully I answered that question for you. So this is what I would be doing. And I'd be storing everything. So a sample for my full conditionals. If I didn't know how to sample from these full conditionals, I could run Metropolis. So I could use the Metropolis-Hastings algorithm. We happen to know in our example that we're playing around with that this is going to be some normal distribution. You know which normal it is. It's going to be centered at the mean of those values, and it's going to have precision parameter, this thing divided by n. So this would be sigma squared k divided by n. So this would be 1 over n phi k. So the same thing, you know what to do. You just write down which one it is. So I'll say the mean average of the x's, k, and it would have this variance parameter, 1 over n phi k t minus 1. So you'd be sampling from that distribution. And you know what this distribution is as well. This is going to be some gamma distribution. And I'll let you work out those parameters. And so you would know how to run this. Okay, here's the rub. We don't actually know what these are usually. So typically, we don't get to observe the KIs. So in typical mixture sampling, when you do all of this, if somebody told you what the groups were, it would be pre-stratified for you, and you could just compartmentalize everything and just update these parameters independent of all of the data, because you would know which data conform to which component. So I want to remove this, and all you get to see is the histogram. So you get to see your histogram of data. Something like that. Try to make that look a little bit more histogram-y. And so you just see this blob of data right here, and you know that there's groups. And so if you try to infer everything, assuming that this data came from one normal distribution, you go terribly wrong. You'd be able to talk about what's going on average, but even your probability measures and your intervals wouldn't be correct because a one-component normal distribution doesn't have bumps in it. So it's not multimodal. And so that would be a bad inference. So if you ever look at your data and you see grouping effects, then this is a case where this mixture sampling thing that I'm about to tell you would be very, very useful. I will say in general, modeling things with normal mixtures is kind of nice. So if you use enough normal mixture components, you can almost reconstruct the shape of any distribution. And so why? They're symmetric, they're smooth, and so I can kind of combine them to come up with really funky shapes and distributions. I do it all the time. Let me give you another example. Let's say you're trying to treat patients that have something like COVID, or some other disease, whatever it is, and you notice that the responses, how well they do, so maybe this is a wellness scale, has some clustering in there, some grouping effects. And so what happens in medicine is not everybody responds the exact same way to different remedies. So in COVID, I'm not an expert, but I can imagine that different subpopulations are going to respond differently for a number of different reasons. It could be diet, it could be their genetics, so for instance, their blood type. So our blood type is defined by different antibodies. If anybody wants to know, I'm O negative, so I'm a universal donor. And it turns out that my immune system is fairly robust to the flu. And some people without O-type bloods might be more susceptible to other types of flus. So people are different. And so in personalized medicine, the idea is to figure out which group you're actually in instead of just giving you the same medicine that they give to the entire population. So I think when we're dealing with people and stuff like that, not well-controlled systems, a lot of times we do see things appear like they're coming from a mixture distribution. Some people call this clustering. So what we'd need to do is identify the clusters, and then we'd have to identify the driving parameters in those clusters. For a Bayesian, we do that all very jointly. So that's what I'm going to show you how to do. Okay, so we're going to remove the K's. You don't get to see them. If you do get to see them, supervised learning, it's great. So you can train on it. So let's take away the K's. And basically what we need to do is just learn them. How does a Bayesian learn something? They build its posterior distribution. So pretty straightforward. We need to learn which K, this is an element of our cap K components. we need to learn which of the k's is responsible it's a word that they'll use in the machine learning community for doing this. If you use that word, that's fine, but what we're actually going to be doing is building a Bayesian posterior, and that's what I see them do as well. They'll call it the responsibility index. I call it a posterior. So we'll see what I mean in a moment. It's the exact same thing no matter how you say it, though. So we need to learn which k is responsible for creating each of the xi's. We need to do that for all of the data points. Now, what I want to tell you is that if I knew what the mu's and the phi's were, this would be an easy problem. So, I'll make a note. If we knew the mu k's, I'll say mu k and phi k, which is 1 over sigma squared k, then this would be straightforward. So I said something else was straightforward at the beginning of the class. I said, if I knew the k's, then I could learn the mu's and the phi's through this algorithm. It would be straightforward to figure out what those are. Now I'm going the other way around and saying, if I knew what the mu's were in the phi's or the variances, then learning the k is relatively straightforward. Let me show you how to do that. So learning ki's given mu k and phi k. We're going to say this is going to be for all of the cap k parameters. So there's going to be 2 parameters that we're going to condition on. We've got cap k of them, and so we have cap k times 2 things that we're conditioning on. Okay, how do we do this? It's just Bayes' theorem. So remember what we have. We know what our sampling density looks like parametrically. In our case, it's going to be a normal. I'm just going to write it down more generally. Fx given theta k. And I'm going to change my notation a little bit. So I'm going to define this to be Fx given theta k. And I'm going to be a little repetitive with my notation. And I'm just going to condition on k itself. Now, this is redundant because you know the k right here. But I just want to build in some notation for you. So I'm just going to redefine this. So in our example that we're playing around with, we're going to have nx given mu k and phi k, 1 over sigma k, if you'd like to parameterize it that way. This is going to be, I'm going to write it down this way, x given mu k, phi k, and k. So I'm just going to define it to be that. So what does this look like? Same thing as it did a while ago. I'm just changing my notation that I used to represent all of this. So this is going to be phi k
to the 1/2, e to the minus phi k divided by 2 times x minus mu k squared, and that's everything.
So it's just that density function that we had from the very beginning. I haven't changed anything. I've just kind of changed my notation. But it sets us up for a Bayesian analysis. So let's just refer back to this right here so we can write it all down more generally. And then we'll do everything for our actual normal example. So we're going to iterate between talking about it generally and then move into our specific example. Sierra, how am I doing on time?
It is 12:53.
Okay, plenty of time. This might be the most useful thing I'm going to teach you here, this and the model selection component to the class. So if you don't have time to play around with this for extra credit, keep it in mind for the future. So if you're doing a lot of data analysis, you are going to come across this sort of mixture identification problem. But how do we learn K?
I should say, how does a Bayesian learn K?
And the answer is through its posterior. Remember that I'm pre-assuming that I get to know these right here. So let me redraw my picture. Well, imagine I've got a 4-component mixture model. So this is going to be mu k right here, mu1, mu2, mu3, mu4, if you will. If I do the mu's, then all of the x's are conditionally independent of each other. And so they don't help me to learn anything. So if I already knew what the parameters are, the data is conditionally independent. And so to learn what k is, all I need to do is use one data point. So it's associated data point. So let's say I saw a data point right here. Let's say that was xi. Which component would I think this is in? I probably think this is coming from component 1. I probably don't think that it's coming from component 4. And so I could put a probability measure on that. How do we do it? We use Bayes' theorem. So, and I'll say this is specific for ki. And so which x's inform ki? In the presence of mu and phi, only xi is informative. And so what I would do is I would sample ki from its posterior distribution, pi ki, say k, given mu k, phi k, and xi. So I'll make a note. Given mu k and phi k, only xi is informative about ki, our label. Now, I said a Bayesian does it this way. Everybody does it this way. They just don't tell you they're using Bayes' theorem sometimes. So what they do is they build a posterior like this. I write down, I'm going to write it through more generally right here. F, well, let's just do it with the normal example. So I just take my normal xi, condition on that. I plug in mu k, phi k. I'll write in k right here. And then I need a prior probability on k. And then I'm done right here. So let me label this. This is going to be my prior for k. And this will be my likelihood function. The likelihood function seems rather simple here simply because it only has one data point in there. I'll give you some notation for this in a moment. What I would do is I would also marginalize over all of my k's. So in our case, this would be equal, since I normalized everything. Let me just write this down in general. I told you I was going to do this one first, but I went to our specific example first. So in general, I would take Ki, and I would take it from whatever my sampling density was, f, xi, I would plug that thing in, I would have my parameters, theta k, and then I need a prior probability on k. And so, and I can normalize everything. So this is going to be going from k to 1 to cap k. Let me change this. I think I'm not using the right notation this very second. I would do this right here, that's correct. And this thing right here is the probability, I should say, that of k given xi. And this is conditional on mu k and phi k. So this is the probability that k is equal to whatever k I've plugged in here. Now I've used the dummy index down here for k. So these k's right here are not that k. This is a specific k. So let me be a little bit more specific. And I'm going to put a star on there. I'll say this is a specific value of k. I'll write this out more specifically in a second. But in general, this is going to be the probability. I'll put a star here. Oh, and I should write down this notation using my more generalized notation. So this would be a star, this would be a star, this would be a star. And these would be stars as well for that specific k. So this would be the probability of k star given xi. Theta k. So I would be able to do this for each one of the possible k's. So in our 4-mode example, I would have 4 of these probabilities that I can write down. And to sample from it, I would sample from that 4 probability distribution. It's just another multinomial distribution. So let me just say what I've said already. I'm going to recap. If I knew what the mu's and the phis were, then I could compute the probability of each data point coming from a particular mode, and I can compute what that probability is over all of the different components. And so I would do this for each one of my i's. So I'd update all of those. Okay, so let me be real specific about this. Give myself a little bit of room. And show you what this draw looks like. So, Ki will be coming from a multinomial distribution. And this would be all of my posterior probabilities. So this would be the probability that K is equal to 1 given Xi, mu1, phi1. And if you'd like, I can plug in, well, I'll leave it just like that. I have another one, probability that K was equal to 2 given Xi and, whoops, that's a 1. Xi mu 2 phi 2. And I'll continue right here. Take this all the way down to probability K is equal to whatever cap K is. In your extra credit, it would be a 4. Given Xi, mu cap K, phi cap K. So this is a K-sided coin flip. And I would do that for all of my data points. Let me write down what this probability is for your specific example. So this one, for cap K, it's going to look like this. 1 over root 2 pi. This would be a phi K to the 1/2 e to the minus 1/2 xi minus mu k squared divided by, oops, I'm on precision scale, so I'll go phi cap k. This is cap k. This is cap k. So this is my likelihood times my prior divided by the sum of all of these things. So that there are numbers that live between 0 and 1. So this is my likelihood. And this thing is my prior. So I told you at the very beginning of class, this whole class is just likelihood times prior. And that's what it is every single time for a Bayesian. Of course, there's things like Gibbs sampling and what do you do all with everything, but in general, a Bayesian is just writing down likelihood times prior. This will be phi to the cap k over 2. This is just a dummy argument, k, that I'm indexing over. Xi minus mu k squared, and that's everything. So this is a probability. Some people will call this the responsibility index. So in machine learning, people will say, this is the responsibility index for everything. If you're using something like the EM algorithm, you also do this exact same step right here. If you're a non-Bayesian, you call it something other than the posterior. But I'll always come in and say that's a Bayesian posterior distribution. The big question is what do you pick right here? So how do you choose it? If you knew what the pi k's were, if somebody told you up front what the pi k's were in the original sampling algorithm, then you would use that. If you don't know what they are, then you might use it to be uniform. So I'll just make a note, is you might pick pi k equal to the pi sub k's that we had in our original model, if you knew what they were. A lot of times people won't tell you. But you might have some idea. Say you were trying to create something like a spam filter. So there's only two possibilities, spam and not spam. And if you knew about how much spam you got, so I get a lot more spam than non-spam in my email filters, then I can maybe use what I pre-thought the level of spam was, and I could tune all of this and maybe do a little bit better. If you don't know them, and you want to be objective, maybe you just pick pi k to equal to 1 over cap k, and this would be the uniform prior. Ah, yes. Sierra just told me I'm missing my prior down here. So if we use the uniform prior, then they cancel out right here. And so what I've seen people do in either the EM algorithm when they do this step, or the machine learners that don't want to say posterior distribution, a lot of times I use a uniform prior right here. They don't tell you that it ever happened, and they're just looking at the likelihood functions. So they're just using the sampling density to do everything. But basically, this is the one step that you need to do. And so what you would do is, at every step of your Gibbs sampler, I would first update all of my KIs. Once I've done that, then I know for that step of the Gibbs sampler what X's are associated with the different components. So at each step of my algorithm, I can learn what the K's are, and then I can learn what the mu's are based off of those. So what I would proceed in doing is I would sample now for each one of my different modes. Say K goes from 1 to cap K. I would build that other Gibbs sampler that we had written down previously, that I had written right here. So what I would do is I would sample my mu K's. At the tth iteration, I would take this from its posterior distribution. So this is going to be given phi K, t minus 1, and I would condition on my x's for each k. How would I know what these are? I would learn them from this block right here. So I'd have to reshuffle the data every time and update which block I think it's coming from. I would have to condition this on my previous samples as well. So what I would do is I would be updating these at each step. I'll fill that step in just a second. So phi k, I would update from its posterior distribution, phi given mu k at the tth iteration, and I would condition on the data in component k that I just learned from this previous step. And so just remember what we said is if we knew what the KIs were, we could run this algorithm. If we know what the mu's and the phis are, we could do this. Of course, we don't know what those are right here. And if I knew them, I wouldn't be trying to learn them. And so to complete this, I just need to condition on all of these parameters as well. So I'm going to say this is at t minus 1, t minus 1, t minus 1, t minus 1, t minus 1,
t minus 1. And just for completion, I guess I'll plug them all in right here, just so you can see them. T minus 1s. My previous data point, my previous draw from my Gibbs sampler. T minus 1, T minus 1, T minus 1.
Okay, so I'm going to recap one more time. If I knew what the mu's were, but I don't know them, but I can initialize some values for them, then I could learn the KIs, what the Ks were. And I would be updating these Ks. This would change in every iteration, which would change the data sets right here that I'd be conditioning on at each iteration. So I would learn Ks, and then I would iterate, and I would try to learn the mu and the phi. And then I would iterate again. Given the mu's and the phis that I learned down here, I would rerun this loop. And I'd learn the Ks. And then I would learn the mu's and the phis. And I would just iterate over and over and over again. So at the end of every draw, down here, you have a joint sample, once this thing starts to converge, from the joint posterior distribution. So you would end up having joint samples from the posterior for all of my mu's, all of my phis, and all of my, so I'll close that right here, K goes from 1 to cap K, and then I would also have all of these, K1 down to Kn. Where the Ks, again, go from 1 to cap K. I guess I would just have these right here. So everything here would be conditional on the full data set. We can't do that joint sampling in one step. I guess we could use Metropolis to do something like that, but it would be pretty untraditional. And so this is just a new layer to your Gibbs sampler that you're adding in. And so you can change anything in a Bayesian hierarchical model just by adding one line to your Gibbs sampler. Now I say that a little bit facetiously. Of course, we need like more lines in there so we can rejuggle our data, recompartmentalize it. And so there is implementation that you have to think about, data management and all of this. But if you run this, you will learn what the mu's are and the phis. And you'll also learn which data points are associated with which clusters, which groups, which components. I think that's the right way to approach this problem. So we first touched this problem and we played around with some hypothesis testing, which showed us how different procedures work under models that aren't correct. And I think in most statistics, this is the game, that we have a model that's not correct and we're going to try to learn the parameters from it. I don't like the hypothesis testing setup in all of this. I kind of like just learning what the model is. So what is your model? What was the model? And this is probably the most flexible class of models that you can think of. You can change what the parametric form of the components are if you'd like. Sierra does some research where she has different forms in here. She has a whole bunch of normals and then she has a Cauchy. And that relates back to that discussion on hypothesis testing that we were doing earlier. So I guess what I want to say is that to a Bayesian, while everything is likelihood times prior, it usually is writing down a bunch of full conditionals and sampling them. Then once you have your joint samples, then you can infer anything you want to infer, forecast anything that you want to forecast. Apologies for going over for a couple minutes. I'm going to assume I'm going to go over for a couple minutes next time when I just tell you very briefly about Empirical Bayes. And so it's a neat technique, and we'll stop with that. So I think that's it for now. Thank you very much.